All right, so a couple questions here. I just want to make sure on the 3.2 stuff, just because we got, this is when we had so many missed days and things. I want to make sure everybody, if you have any last minute questions on these. So when you have a question like this, does this make sense? Find the value or values of C that satisfy the mean value theorem equation, right? In the conclusion of the mean value theorem for the given function and interval. So let's kind of review mean value theorem. Mean value theorem says what? If a function is what? Smooth. So if it's continuous and differentiable, so smooth, on an interval, right? So if we break that into parts, and in calculus, MVT just means mean value theorem. That's the way it'll probably be in college, right? So mean value theorem, the if part, right, the conditions you have to meet are f is continuous on the closed interval, right? And what was the other one? Good, good. Differentiable on the open interval. Good. So if you meet those conditions, then it's an existence theorem, right? All it does, it doesn't do any of the work for you, but it guarantees the existence of a place. Call it C of an x value. Such that this is true. Right? Such that the slope of the secant line connecting the endpoints of the interval is the same as the slope of the tangent line at the value of C, right? So what we have to do here is we have to decide, first of all, do we meet the conditions of the mean value theorem? So for f of x equals the square root of x minus 6 on the interval, closed interval from 6 to 12, is it continuous?
Yes.
It is, yes. Right? It's in the domain of this function, isn't it? And the function's a square root function. We know what that looks like. That's a continuous function. Is it differentiable?
Yes. Yes.
It is. It is differentiable, right? There's no sharp corners, nothing weird going on. Remember that to say that it's differentiable, this is really a cool relationship, but it's been so long since we talked about it. For a function to be differentiable, that just means that the derivative is continuous, right? You get that? So if when we start doing this problem, if we weren't even sure for some reason, if it was a really weird function, like maybe in college you're dealing with a harder function, and we were taking the derivative because we have to anyway to find those places, right? So f of x, how would I write that to be able to differentiate it? Square root of x minus 6. 1/2 power, there you go. Good. So what's f prime of x then? So I get 1/2 times x minus 6 to the negative 1/2, right? I got to subtract 1, which puts it on the bottom, right? And so now we could just look at this derivative function and ask ourselves, okay, well, is the derivative continuous on that interval? Yeah, it is, right? On the open interval, right? The only place, where is the derivative defined? Well, the derivative is defined for any value of x that is greater than 6. I can't do 6 because I get a 0 on the bottom, right? Everybody see that though? The domain of the derivative looks like that. And so, yeah, it is differentiable on the open interval because the derivative is continuous on that open interval, right? So then all we'd have to do is just go figure out where that happens. Okay? So what's this look like? F of b, you can set up an equation. F of b, square root of 12 minus 6 is just the square root of 6, right? So I'm going to get square root of 6 minus f of a. Square root of 0 is 0 over 12 minus 6 gives me square root of 6 over 6, right? And I want to know where does that equal f prime of x. And wherever it does, we'll call those values c, right? So there's our equation. So we just gotta solve that, right? How would we probably solve that?
Factor the square root of 6 out that one side. That would be the 1 over square root of 6, and we can flip it. So that way we got square root of 6 equals 2 square root of x minus 6.
So you're just taking reciprocal of both sides.
Yeah.
That works. What else could we do? Cross multiply. Let's just do that. So if I get 2 radical 6 times the square root of x minus 6 equals 6, right? If I divide each side through by 2 radical 6, the square root of x minus 6 equals 6 over the square root of 6 is just square root of 6, right? And then what, now what? So I'm solving a radical equation. This goes all the way back to like algebra 2. Square both sides, but what happens if I square both sides? Well, I gotta be careful because I could introduce extraneous solutions, right? So if we square both sides, I'm gonna change colors here so we know we did something important. If I square both sides, I'm gonna get x minus 6, and over here I'm gonna get 6 over 4, right? So what is that, 3 halves? So if I add 6 to both sides, I'm gonna get 6 plus 3 halves is what, 15 halves? Right? Okay, but we did square both sides, so technically what would I need to do here?
Go back.
Yeah. You gotta go back to there, right? To the step before, previous to taking both sides to a power, and check it out. And if I do that, it should work out fine. 15 halves minus 6 is gonna be, what'd that work out to be? That's gonna be 3 halves, and the square root of, so the square root of 3 halves, we can show that's the same thing as square root of 6 over 2, can't we? Right? You get square root of 3 halves is the square root of 3 over the square root of 2. If I multiply top and bottom by radical 2, I get 2 on the bottom and square root of 6 on the top. So it works. Right? Okay. Make sense? Okay. You know, I'm probably gonna, I know we did one like this. I'm probably gonna skip this. We can, if you want it in the future, we can always come back and do one like that. The last 2 problems I want to do, let's see. There were 2 of them. I know I made 2 of them. It's a note to me. You tell me if this is something you want to take a quick look at. Oh, here we go. Oh, yeah, these are good. Yeah, that's pretty cool. Okay, so. Okay, so here's the question on this one. Just make sure we all understand. It says an ancient warship once covered 187 sea miles in 22 hours. Explain why at some point during this feat, the ship's speed exceeded 8.2 knots, so that's c miles per hour. Okay. How does that relate to what we're just doing?
0, 0, and was like 187.
Yeah, don't give me numbers though, I wanna know concepts here. Why, how does that relate to what we were just doing?
It's gonna be accelerating.
Okay.
Shot speed.
Okay, sure, but still, I would claim, I wanna know something more than that. I wanna know, how is that anything like what we talked about here with the mean value?
If the slope is greater than the.
Slope of what?
The speed. Graphing speed.
So a line graphic, so what the mean value theorem says is that if a function is continuous on a closed interval and open and differentiable on an open interval, then there's some stuff that's true. But we just got what's the function here, right? In order for this to be a mean value theorem problem, we've got to be able to see that there's some kind of a function going on here. Now they didn't give it to us, right? But what is the function that we're talking about?
Distance over time.
Okay, so maybe like a distance formula, would agree? The function that we're talking about is the distance covered by the ship. Agreed? Okay. So the distance covered by the ship, it travels 187 miles in 22 hours. Okay, is that a continuous function?
Yes.
Yeah, prove it.
They can't teleport.
You can't teleport, exactly, right? Would you agree that if the ship is gonna go from there to there, 187 miles away, it has to cover every point in between? It can't jump over points, can it? That's not the way the universe works on a macroscopic level, right? So, yeah, it does work that way, it's small enough. So it is, so the distance function is continuous from 0 to 187. Okay, so now, is it differentiable? What's the derivative of position or displacement? What is it? Velocity, right? The derivative of position is velocity. So the position function is continuous. Is the velocity continuous? Is it differentiable? It is. Prove it.
You can't instantaneously switch between disparate speeds.
You can't instantaneously jump from one speed to another, right? It doesn't work that way. You have to accelerate smoothly from one speed to the next. You can't just automatically go from 0 to some speed, for example, in the blink of an eye, right? Okay. And
They're still decelerating.
I mean, if you're physics types, I mean, that's pretty easy to defend because that would require an infinite acceleration, which would require an infinite force, which would require infinite energy, and none of that stuff works, right? So we know that, but with the point I want to make with a problem like this is that you can take this really abstract physics concept, this mean value theorem, which seems like just a paper and pencil kind of a thing that has no bearing on reality, but it does provide a pretty immediate proof, that this has to work, right? It still fulfills those conditions. If you define the function as the position function, then it certainly is smooth on the interval from 0 to 22 hours. I guess that's what we're looking at. Right? Position is as a function of x. So if that's true, then what are the conditions of the mean value theorem? Well, then we know that the average rate of change, the slope of the secant line, at least at one point, has to equal the instantaneous rate of change, the slope of the tangent line, right? So if we were to draw a picture of this, wouldn't it just look like this, right? We've got our position, let's just call it x. Say he's moving in a straight line along the x-axis along the ocean. We'll just define the x-axis there. And this is t. And we're going to go from 0 up to 22, right? And so what's this thing going to do? Well, I don't know. Maybe it's going to look something like, that. Maybe. Who knows, right? So A equals 0, B equals 22, right? if we want to calculate what is the average rate of change, so x of 22 minus x of 0 divided by 22 minus 0. Well, what's x of 22 based on the problem? How far has it traveled after 22 hours? 187 miles. How far has it traveled after 0 hours? 0 miles. 22 minus 0, so we end up with 187 divided by 22. Somebody, what is that real quick? Hey, Michelle, what's up? Yeah, he just left. I think he, yeah, okay, bye. Okay, bye. So what is that, roughly? 8.5. 8.5. And that was miles per hour, right? Nautical miles per hour. So then, how come, defend the reasoning here, defend your answer. So why do we know that it has to exceed 8.2 knots? Yeah, you can't skip numbers, and what did it start at?
0, 0.
Yeah, started at 0, ended at 0, right? So you know that at some point, it has to go, well, it doesn't even matter what it started at. You know that at some point, it has to go 8.5, right? So 8.5 is bigger than 8.2, right? It doesn't ask us where. We don't know where, we don't know what the function is, but it just tells us, it guarantees the existence of that place, okay? All right. Okay. I made this a few days ago, I gotta remind myself why I did this. Graph of the, okay, yeah, that gives us the graph. Question?
So if you can't skip over speed, how do you ever get to like the next one? Like if I'm going 4 miles an hour and I want to get to 5 miles an hour, how do I ever get that?
Okay, let me throw that question back at you. By that logic, how could I ever go anywhere?
No, I get it. I
See what I'm saying?
Yeah.
How could you ever go anywhere? Because you have to, it's kind of a paradox in a way, because you have to cover, you can't skip any points, so you have to hit every point in between, but between each point, there's an infinite number of points, right? It's just kind of it's just a fact that we have to accept, that you can have finite speed and still cover an infinite number of points, right? Because distance isn't dependent. Here's my best explanation. It's a good question. Distance is independent of the number of points between the beginning and the end point, right? Beginning point and the end point. All that matters is distance is an arbitrarily definable quantity that doesn't depend on the size of the infinity in between, right? It's only the end points. Does that make sense?
Yeah.
And so for that reason, you have to be able to, I don't know how else to describe that without thinking about it for a while. That sort of semi-satisfying to you? Okay. All right, what about one like this? So the following figure gives the graph of the derivative of a continuous function f that passes through the origin. Sketch a graph of the function on the same set of axes. Okay? So let's get the shape of this thing first, right? What do you know? If this is the derivative function, that's what they're giving us. In fact, let me write that down here. This is f prime. If that's the derivative, what are some things you can tell me about the function? So it's going to be cubic, yeah. Good. So what's going on here? What's going on at that place right there? What's the value of the derivative? 0. So what's that tell you about the shape of the curve? It's got to have a horizontal tangent, right? So can we be very specific about this? I mean, not super specific, because we don't really know what this function is. But we know that this one has to have a horizontal tangent at that value. It also has to have a horizontal tangent at that value, right? So those are places where we get, let's call it HT for now. Okay, what can you tell me about this region in here? What's the sign of the derivative there? Positive. So if the sign of the derivative is positive, what's the function doing? It's rising. Okay. What's the sign of the derivative over there? Negative. And it's getting increasingly negative, isn't it? So it's falling and it's getting steeper, right? Same thing over here. In that direction, we get a negative derivative, right? So now, if we wanted to graph this thing, what does it have to look like? What is this point going to be if it's a horizontal tangent and it's a transition from a positive slope to a negative slope? It's got to be a peak, doesn't it? Right? By our first derivative test, you see that really what that's telling us is that this horizontal tangent is occurring at a peak, right? So that's going to be something like that. If we're at a point of transition, we have a horizontal tangent where the derivative is transitioning from negative to positive, that must be a valid, right? So all we got to do then is, our goal here was to draw a function that has these characteristics that passes through the origin. Somebody want to try that? Go up to the big board and try that, anybody? All right.
So want me to just draw the original equation?
Yeah, just draw the original function. Yeah. Yeah, that's the right idea. They to just be a little nitpicky, they wanted it to pass through the origin, right? So probably the only thing we would have done differently is maybe just like right here, we know that we're going to get along that vertical line, we're going to get, whenever we get to that x value, it's going to be a valley. So it's going to look maybe like that. This one's going to be a peak. So maybe it looks like that, and then it just has to come back down through the origin. But you get the idea, right? Does that make sense? Okay, and then when you see these kinds of questions, I gave you a few of these on math, so I think these are really good questions to do, especially good if you're going into like engineering or physics or things, because it forces you to make this connection between, you know, like for example, kinematic stuff would be between acceleration and velocity and position, right? So, which one of those fits the bill? I guess it'd be that one right there, wouldn't it? Right. Okay, everybody see that?
Yep.
Okay. And once again, just notice, just want to make sure you get so that the zero of the derivative function, the purple function, corresponds to a horizontal tangent, so a turning point, we call that, right? Minimum or maximum of the blue original function, okay? How about something like that guy? Use the graph of the derivative function to estimate the intervals on which the function is increasing or decreasing, okay? So this is now what's easy to do with these. It's so easy to our minds are telling us, because we've been taught for so many years, that if I graph a function, it's the function, but it's not. It's the derivative of the function, right? We're the different calculus scenario here, right? So if that's the derivative, on what interval would this function be, or what intervals would this function be increasing?
1 to slightly less than 2. I mean, slightly less than 3.
So we're talking about f. F is increasing on,
Approximately 1 to 2.5.
no. Because you're doing exactly what I was, see Tyler's, he's fallen into that trap of falling back to pre-calculus thinking.
Maybe to 0 and 2 to 3.
Okay. Negative infinity to 0. Now, open or closed? Open. Open, good, because it's not happening at 0, it's not increasing or decreasing, it's a transition point, right? Comma.
2 to 3.
2 to 3. Everybody see that?
Yeah.
Okay, we're just looking at the places where the derivative is positive value. That's a simple relationship, but it's hard to, it's kind of hard to conceptualize that at first. Where the derivative is positive, the function increases. That's simple. Where the derivative is negative, the function's decreasing, right? So it's going to be decreasing on what? 0 to 2 or 3 to infinity, right? Okay. How about this one here? Find the locations of all relative extrema of f of x. Tell whether each one is a relative max or a relative min.
Well, the derivative is 0.
So negative
So,
7, negative 5,
okay.
negative
So we're gonna get,
3, and negative 1.
so here's gonna be one place, I'll kind of color code these, so that point right there, that's a transition, isn't it? Remember, the derivative is 0, we're gonna get, those are some places where we're gonna end up getting peaks and valleys, right? So what's that one gonna be? The red one at x equals -7, what do we get, a minimum or a maximum? And why? What do you think? What do you think? Julie, what do you think now? This is the derivative function here, so we're looking at it's graphing slope, right? So this is a place where the derivative is going from positive to negative. What's that gonna be? It's gonna be a peak or a valley. Going from increasing to decreasing. That's what I'm going from. Now, it looks like a valley because this thing's going downhill, right? But positive values of the derivative, think what that means. If it's a positive value of the derivative, that means the slope is positive. So that's a really steep positive slope, less steep, 0. So what that means is think what that would look like. It's going uphill very steeply, and then it's going to 0, and now it's becoming more negative. So it's gonna look something like that. Does that make sense? So that's a relative max. What's happening here? What's happening there? It's got to be a valley because I'm going from decreasing slopes, so it's going to look like decreasing to 0 to increasing, right? So at x equals -5, relative min. What about, so where else would you get them? So -3, that's gonna be, once again, that's gonna be a max, isn't it? Right? And at -1, that's gonna be a min. Agreed? Okay? What's going on down here? Anything important?
It's not differentiable.
But this is the derivative. So the function must have been. It looks like it's nothing special. I think what it's doing is the slope is getting more and more negative, and then it starts to get more positive again. We can do that, right? It looks like it'd be something crazy, but it's not. How could we get a sharp corner on this? Place where the derivative doesn't exist, what might that look like? None of those showed up on there, did they? How can I get a sharp corner? Say it again. Well, of the derivative, you're right. It wouldn't be. No, that's true. Think about that a little bit. But let's say we want to get out here at x equals 4. I want to graph a derivative that's going to give me a function that has a sharp corner. Yeah, it might look something like this. What if I did? Well, I could make it really simple. I could just do something that goes like this, right? What's that going to look like? If I were to graph that function, I've got a positive slope here and a negative slope here, so wouldn't that just look like if I actually, this is f prime. If I graph the function, it would look something like maybe, something like that, wouldn't it? Right? I get a constant positive slope to the left and a constant negative slope to the right. Okay? Make sense? So the derivative is undefined there. Okay?
So, so the graph above is when the derivative
That's the derivative, right?
So then what would the, is that what the function would then?
No, so this function, this function, let's try the function. If we wanted to just graph this function up here, what would it look like? I mean, it's not gonna be exact, but we can get a pretty good idea. So we know we're gonna get we're getting maxima at -7, so we'll put that guy up there, and at -3, so like right there, and we're getting minima there and there, right? So all this thing is doing, it just looks kind of like this. Yeah. Just essentially looks like that. Now this thing here, this is going to be a little bit, I'm trying to figure out what that's actually going to do. So it's going to get more and more negative, so it gets down to some maximum negative value right here. And then, yeah, it just would look kind of like that. I don't think it's going to look like anything crazy. Yeah, it's going to get, right, and I wasn't that precise, but like it's going to be the steepest, right? It should be the steepest if I had drawn it correctly right there. Right, I didn't draw it. I didn't take that much time. You get the idea. That's a good point. So, yeah, it'd probably do, it'd probably like curve down really hard like that, and then it would start to maybe do something like that, yeah. Okay? Okay. So then the other thing I wanted to just briefly introduce you to get your brain activated on